Out there, beyond the calm glitter of familiar constellations, something blinks. Not with the soft rhythm of a distant sun, but with the precision of a heartbeat made of lightning. Every few seconds, a burst of radiation cuts through space, a pulse so intense it could erase an entire planet if it came too close. It is ancient, it is small, and it is terrifying. NASA watches it every hour of every day, because this single spinning ember may hold the key to both the birth and the death of stars, and the limits of what matter itself can survive. A star's last breath. Long before it became a cosmic beacon, it was a giant, a blue-white sun more massive than 20 of our own. For millions of years, it burned with impossible brilliance, its core fusing hydrogen into heavier and heavier elements: carbon, oxygen, silicon, iron. Until one moment, when physics itself ran out of options. Iron cannot fuel fusion. It consumes energy instead of giving it. When the core filled with iron, the balance broke. Gravity won. In less than a second, the entire star imploded, a collapse so violent it crushed atoms, shattered nuclei, and rebounded outward in the most powerful explosion known to science, a supernova. For an instant, it outshone entire galaxies, and when the light faded, what remained was not a star, but the ghost of one. The birth of the impossible. What survived that explosion is called a neutron star, an object so dense that a teaspoon of its matter would weigh 1 billion tons. In that collapsed remnant, protons and electrons are forced together until only neutrons remain, a single planet-sized atomic nucleus spinning tens of times each second. Gravity is so strong that light itself bends around it. Magnetic fields so intense, they could strip electrons from atoms thousands of kilometers away. And yet, this monster is only 20 kilometers wide, smaller than the island of Manhattan. It should be silent. It should be still, but it isn't. The first pulse. In 1967, two young astronomers, Jocelyn Bell and Anthony Hewish, noticed a repeating signal on their radio telescope, a pulse every 1.3 seconds, too regular to be natural, too faint to be man-made. At first, they called it LGM-1, Little Green Men. But soon, more signals were found, different periods, different locations. The universe was full of them. They were not aliens. They were pulsars, rotating neutron stars whose magnetic poles act like cosmic lighthouses, sweeping beams of radiation across the cosmos. Each pulse we detect is a flash from that beam as it crosses Earth. A cosmic heartbeat, marking the rotation of a dead star. The monster among pulsars. Most pulsars are stable, predictable, almost gentle in their regularity. But among them lurk rarer, far more violent cousins, magnetars. If a neutron star's magnetic field is already 1 billion times stronger than Earth's, a magnetar's is 1,000 times stronger still. Here, matter itself is tortured. Atomic bonds twist, space around it crackles with quantum tension. When that tension snaps, the star releases an eruption called a starquake, a burst of gamma rays powerful enough to rattle satellites on the other side of the galaxy. One such blast once ionized Earth's upper atmosphere from 50,000 light-years away. Imagine what would happen if it were closer. NASA calls these stars cosmic ticking bombs, and there are only about 30 known in the entire Milky Way. The star that keeps scientists awake. The most notorious of them is catalogued as SGR 1806-20.
It sits in a cluster of young, massive stars on the far side of our galaxy, obscured by clouds of dust and gas. From Earth, we cannot see it with optical telescopes, but X-ray and gamma-ray observatories pick up its flashes like gunfire in the dark. Every few seconds, it emits a pulse. Every few years, a quake shakes its crust and floods space with radiation. On December 27, 2004, it exploded. For less than a second, it released more energy than the Sun produces in 150,000 years. Satellites around Earth were blinded. Auroras danced near the equator, and for a heartbeat, our planet's magnetic field wavered. If SGR 1806-20 had been 10 light-years closer, the pulse would have stripped our ozone layer completely. NASA now tracks it continuously, along with a handful of others whose tantrums can reach across half the galaxy. Why so dangerous? To understand why these stars are so unstable, we must look inside them, into physics so extreme that even our best equations begin to fail. The surface of a magnetar is a crust of crystalline nuclei, compressed until the gap between atoms disappears. Beneath lies a sea of superfluid neutrons, matter so dense that it behaves like a single quantum object. Through that sea, magnetic fields thread and twist. When they shift, they drag the crust with them until it cracks. That crack unleashes magnetic energy billions of times stronger than any human weapon, firing jets of X-rays and gamma rays across the galaxy. It's not just dangerous, it's beautiful. A deadly ballet of matter, magnetism, and mathematics. NASA's 24-hour vigil. Since 2004, NASA has maintained continuous observation of known magnetars. Satellites like SWIFT, Fermi, and the Chandra X-ray Observatory constantly scan the sky for bursts lasting mere milliseconds. Most flare without warning. Some emit a sequence of short pulses, as if the star is echoing its own heartbeat. When a new flare is detected, alerts ripple across the planet. Ground telescopes, radio arrays, even neutrino detectors swing into action. Each burst is a chance to learn what happens when the laws of nature are stretched to their breaking point. Because inside a magnetar, we glimpse physics that no laboratory on Earth can replicate. The bridge between relativity and quantum mechanics, where gravity and magnetism dance in unison. Echoes in the darkness. If you could stand near one, though nothing could, you would see light itself bending around it. Space would twist. Every atom in your body would be torn apart by tidal forces stronger than those near a black hole. And yet, from across the galaxy, it looks so calm. Just a flicker among millions of stars. A reminder that danger and beauty often share the same light. NASA watches because these stars are not only destructive, they are teachers. Each pulse, each quake, each burst reveals how matter behaves under pressures that crush the boundaries of physics. They are windows into what might happen inside neutron star mergers or the moment a black hole is born. And perhaps they hold the secret to forces we barely comprehend. Magnetism so fierce that it reshapes space-time itself. Transition to part 2. But these are only the ones we can see. Across the Milky Way, countless others hide behind clouds of dust, their beams aimed elsewhere, their tempers waiting. Somewhere among them may lurk the next great outburst, one strong enough to ripple across the galaxy, one that could reach us. In the next chapter, we'll follow NASA's watchful eyes deeper into the data, to decode the signals and uncover what these stars are trying to tell us about the fate of the universe itself.
Every heartbeat in the universe has a rhythm. Oceans rise and fall.
Stars are born, burn, and fade. Even in death, they pulse with memory. For a neutron star, especially a magnetar, that pulse is not calm. It is tension incarnate. Every second, unimaginable forces twist its skin, coiling magnetic fields tighter and tighter, until reality itself begins to strain. And then, it breaks. The moment of catastrophe. Imagine an earthquake, but one that doesn't shake rock or soil. It fractures the crust of a star. That's a starquake. The solid surface of a magnetar cracks under the stress of magnetic distortion. When it snaps, energy equivalent to billions of nuclear bombs bursts outward in less than a second. Gamma rays surge through space at the speed of light, a wave of pure radiation sweeping across the galaxy. For any world too close, it would be the end. Atmospheres stripped away, ozone burned, DNA unraveling in seconds. Earth is safe, for now, only because the nearest known magnetars are thousands of light years away. But even from that distance, we can feel their anger. The 2004 event, the day the galaxy flinched. It was the morning of December 27, 2004. NASA's satellites, including SWIFT and RHESSI, detected a blinding flash of gamma-ray radiation. For 0.2 seconds, detectors were saturated, systems overloaded. The energy spike was so extreme, scientists first thought it came from a nearby supernova. But it didn't. It came from a single star, SGR 1806-20, a magnetar 50,000 light-years away. For an instant, it outshone every other source of gamma rays in the observable sky. Its brightness briefly altered Earth's ionosphere, an effect usually reserved for solar flares. Astronomers realized that if it had been just 10 times closer, it could have erased the upper atmosphere completely. One star, 1 second, a weapon of nature beyond imagination. That's why NASA watches, because if it happens again, even slightly closer, we may only have moments to understand it. Inside NASA's vigil. All around the world, an invisible network listens to the sky. The Fermi Gamma Ray Space Telescope, the Neil Gehrels Swift Observatory, the NICER telescope aboard the ISS, and the Chandra X-ray Observatory, each designed not just to observe, but to react. When a high-energy flash erupts anywhere in the sky, NASA's alert system activates in milliseconds. Automated signals ripple through the deep space network, triggering telescopes on Earth to focus their gaze. To most of us, the universe looks quiet. But NASA's sensors record a cosmic thunderstorm, dozens of small flares, whispers, and bursts that never reach the human eye. The sky, it turns out, is alive with violence. When light breaks physics. So, what truly happens during a magnetar flare? When the crust breaks, the surface rearranges. A magnetic whiplash sends shockwaves through the magnetar's magnetosphere. Particles accelerate to near light speed, slamming into each other and producing intense X-rays and gamma rays. But here's where things get even stranger. In magnetic fields this strong, 1,000 trillion times stronger than Earth's, quantum laws start to warp. Empty space itself becomes polarized, acting like a crystal that bends and splits light. This phenomenon, called vacuum birefringence, is something no laboratory can replicate. But magnetars demonstrate it naturally, reminding us that the universe can twist the very fabric of nothingness. Even photons, massless, eternal, can be bent by magnetism. The hidden orchestra. When NASA scientists listen to these bursts, they often convert data into sound, a process called sonification. Each pulse becomes a tone, each flare a chord. The result is eerie and hypnotic, a star screaming across 50,000 light-years translated into audible waves. The hum of plasma, the crack of gamma fire, the echo of a neutron crust snapping like glass. Listening to it, you realize this is not chaos. It's music, a rhythm older than biology, the universe expressing itself through destruction and rebirth. The enigma of the anti-star. But magnetars hold deeper mysteries still. Some theories suggest they are transitional forms, that their magnetic energy might decay into something even stranger. In rare cases, when a magnetar finally collapses under its own weight, it may form a black hole, a trap from which not even light can escape. But others speculate there could be another path, a conversion into something called a quark star, matter compressed beyond neutrons, where quarks themselves roam freely. If so, these objects would be the densest form of matter short of a singularity, and perhaps the rarest in the universe. NASA's instruments have picked up signals that don't fully match magnetar physics. Short bursts, narrowband pulses, events that flicker and vanish without explanation. Some scientists quietly wonder, are we witnessing stars transforming into something new, or something forbidden? The magnetic dance of death. Each magnetar is born from violence, and many end that way too. Over tens of thousands of years, their magnetic fields decay, their energy fades, their pulses slow. But before that long sleep, they can erupt one last time. A final flare, a magnetic death rattle that releases every ounce of stored energy in a single blast. If one were ever close enough to Earth, we would have little warning. A flash of gamma rays, a ripple in our magnetic field, communications blacked out, power grids overloaded, then silence. For a few terrifying moments, we would feel what it means to live within reach of a god's anger. But that is precisely why we watch. In orbit and on Earth, scientists stand guard against the universe's most violent moods. They model each flare, calculate each pulse, and trace how energy moves through space-time. Every burst adds a piece to the puzzle of cosmic magnetism, a force that shapes galaxies, births stars, and maybe, in ways we still don't understand, connects everything. Because if we can decode how magnetars bend matter and light, we might learn how the universe itself began, and how it might one day end. Transition to Part 3. For now, the sky is quiet. The magnetarists slumber in their distant clusters, their pulses faint but steady. Yet NASA's satellites never rest. They watch, waiting for the next heartbeat, the next eruption that could rewrite physics again. Because in their silence lies both danger and wisdom. And if we listen closely enough, we may find that these monstrous stars are not our enemies, but our teachers. In the final chapter, we'll explore what these stars reveal about the universe's destiny, and what humanity's constant vigil says about us, our fear, our curiosity, and our unending desire to understand.
In the silence between stars, there is still movement. A pulse here, a flicker there. The rhythm of the universe continues, unseen, yet unbroken. And though those distant hearts burn far beyond our reach, their whispers reach us still. Every photon, every magnetic tremor,
every flare that glances across our tiny blue world is a message from the cosmos itself. We are not the center of the universe, but we are its audience. Eyes in the sky. Far above our atmosphere, NASA's satellites float in their silent vigil. Swift, Fermi, Chandra, Nicer, each an unblinking eye staring into the dark. They orbit Earth not as guardians, but as witnesses. Every few hours they catch another flare, a whisper from a magnetar on the other side of the galaxy. Most are small. Some are bursts so powerful they momentarily drown out everything else in their field of view. Each time the data pours in. Waveforms, frequencies, decay curves, numbers. But within those numbers lies something deeper. A story. The story of what happens when the universe pushes matter to its limits and still finds beauty in the breaking. The art of catastrophe. When a magnetar erupts, it doesn't just release energy, it sculpts space-time. Magnetic lines twist into knots, plasma flares carve luminous arcs through invisible fields. It's as if the universe itself paints with lightning. Physicists model it with equations. Artists imagine it in colors we've never seen. But both are searching for the same thing: to understand the shape of creation. Because in the violence of these stars, we find the same pattern that gave rise to us: the push and pull, the tension and release, the endless cycle of destruction giving birth to possibility. Lessons from the dark. You might wonder, why spend billions watching a handful of stars that pose no immediate threat to Earth? Because they reveal how fragile reality truly is. A neutron star shows us how far matter can bend before it ceases to exist. A magnetar shows us the limits of energy, how magnetic force can overpower gravity itself. And in those limits, we glimpse the architecture of existence. We learn that the laws of physics are not arbitrary. They are the boundary between order and chaos. We watch these stars not because we fear them, but because they remind us that everything, even the universe itself, has an edge. The human connection. Think about it. When Voyager 1 left the solar system, it carried with it a golden record: music, greetings, the sounds of life. And somewhere millions of years from now, that tiny probe may drift past a dead star, its golden disk still intact, glinting faintly under the light of a magnetar's pulse. We build these machines not out of arrogance, but out of longing. We want to understand, to see, to listen. Because even though we are small, we have learned to watch the stars that could destroy us and find peace in their fire. NASA's eternal question. Every generation of scientists inherits a question: what lies beyond what we can see? For the astronomers watching magnetars, the question becomes almost spiritual. They're studying objects that have no analog on Earth, where gravity is infinite, magnetism impossible, and time almost meaningless. And yet every new observation brings us closer to a unified truth: that everything, from galaxies to atoms, obeys the same cosmic rhythm. The same forces that twist a star's crust flow through your veins as electricity. The same particles that erupt from a magnetar once formed the atoms in your bones. You are made of the same story you seek to understand. The light that never dies. Most magnetars will eventually fade. Their magnetic fields weaken, their pulses slow, until they become quiet neutron stars, cold and forgotten. But their light doesn't vanish. It travels outward, crossing the gulfs between galaxies, passing through nebulae, through dark matter, through the cold haze of eternity, until it touches another world. Maybe one with eyes looking back, maybe one asking the same questions we do. In that sense, magnetars are storytellers. Their flares are letters written in radiation, messages that say, I existed, I burned, I mattered. And when we detect them, we answer back with our own kind of light. Our watch never ends. NASA's watch continues not out of fear, but faith. Faith that by studying the most extreme objects in the universe, we will find reflections of ourselves. Each satellite orbiting Earth is a symbol of that faith, that knowledge is worth the risk, that curiosity is stronger than destruction, and that no matter how dark the cosmos becomes, we will keep watching. Because watching is how we learn, and learning is how we survive. In the end, this is not a story about danger. It's a story about attention. A story about how fragile beings on a small blue world chose to look into the storm instead of away from it. We are, all of us, watchers of the universe, seeking meaning in the pulse of stars, and finding, somehow, that the universe is watching back. Out there, a star turns once more. Another pulse, another heartbeat. The universe breathes again. And somewhere, NASA listens.